Okay, now let me define what we call a Wiener process. So definition, or you can say properties of a Wiener process. And basically, there are 4 points that define a Wiener process, or the properties of a Wiener process consist of 4 points. The first point is, if you notice if you remember what I showed you in the beginning, these graphs, right, these simulations, then both curves I showed you started in 0. So the first property is that we assume that my Wiener process, at time 0 is 0. So it starts in 0. And once again, just to make this clear, I can write down here W. W is now my stochastic process. It's like the capital X. Or I can write here the B, right? And then I call it the Brownian motion. That does not matter. It's all the variables I use here now are stochastic processes. And to the fact that it's according to Wiener, I will use the W here, obviously. So the first property of a Wiener process, it starts in 0. So at time 0, the process is 0. The value is 0. Then the second property, the Wiener process, Wt, is what we call almost surely continuous. Well, this is very important, and the short for this is A.S. Yeah, and if you read books, and probably my lecture note, at some point I will not label it always almost surely, I just say A.S., which means almost surely. Well, this indicates, in principle, in mathematics, Newton, Leibniz, they assume continuous functions. They are smooth functions over time. And if there are smooth functions, differentiation and integration is easy to do. But a stochastic process, that is crazy. Sometimes it jumps up from this time to next time. There is no real smooth transition between these two time periods. But we assume, in a way which I will not define, and you can just read books about how can you handle this almost surely and so on. We just assume that this Wiener process W2 it's almost surely continuous. It's not really continuous, but for you can say it is almost continuous. Yeah. So we keep it as a continuous function, but actually it is not. Yeah. It can have some jumps, in other words. The third property is the most important one. Yeah, and therefore let me highlight this with an arrow here. This is the property which we will use later on several times. And it basically says that the increment of a Wiener process, which is the difference of the Wiener process at period t and at period s, let's say t is greater than s. T is greater than s. Yeah. So this difference, we call this an increment of the stochastic process, is normally distributed. Yeah, therefore we talked about distribution, and normal distribution in particular last time, is normally distributed with the following properties, with expectation of this zero, and the variance of this increment is t minus t. So let me explain this. So the change of the Wiener process, right, over time. Now that's over time. We look to two different time points of my process, period t and s. And this change, this increment, is normally distributed. And the expectation is 0. And the variance of this increment is the time difference. Yeah? The difference between the time is the variance. So in other words, if I write down the density function, you know the density function of a normal distribution, let's call it x, we discussed last week. You all remember, well, a normal distribution is 1 over the square root of 2 pi sigma square e minus 1 over 2 x minus mu squared divided by sigma squared. That is the density function of a normal distribution. In this case, it looks a little bit different. What is different? Well, you know the mu is the expectation. And in this case, we assume the expectation is 0. So the mu is 0. The sigma, you know, for the variance, we use also this letter sigma square, which is here, and it pops up here as well. Well, the sigma, as you can see, which is the variance, is the difference over time. T minus s. So if I simplify this and say, well, let's say s, which is the starting point, is 0, yeah, then I can write down this density function for a Wiener process, s, and that is what you sometimes see in books. It's 1 over square root 2 pi sigma square, yeah. For S0, well, that is obviously then t square. 1, and then we have here 0, so we have just my random variable stochastic process x squared, and once again here we have the variance squared for S0, it's just t squared. So this density function is now reflecting the transition density function of a Wiener process. Question?
Please one more time explain why you did ds.
Well, you know, this is just simplification. If I say, well, we make it more general, then we have to write t minus s squared, and we have here t minus s squared, you see. You know, to make it as simple as possible, to save time and whatsoever, I just assume, let's say s is our starting point, yeah, and then we go on, and let's say starting point is 0. It's just a definition. Otherwise, I have a more general term if I say s is 1 or 2 or whatsoever, another starting point. Other questions so far? Yeah?
Just to understand, so when the property second one says that it's almost surely continuous,
Yeah.
and the difference between dynamic function and static function is the flow of the time, so you're assuming that the time is not linear.
No, the time is linear. So, if we have here t and here a function or a variable, let's say x dependent on t. A static, it would have for all the time a certain value. A dynamic function, well, it go up, down, I don't know. But a stochastic function, you know, you can say maybe this is a continuous function, right? There is no gap, but in stochastic it could be, there could be some, you know, it's not as continuous as it is usually. That is what this means. It is almost surely continuous. So you can fill the gaps and then it looks like this. Yeah? That is only what this almost surely means. But don't worry, we are not going in all these details and depths to discuss this. That is far beyond what we can do here. Yeah? Okay, final property. Fourth property. The fourth property is very close to the third one. So the increment, or the increments in plural, the increments, I mean this change of WT, WS, are independent of the past. So if I have a sequence like this, WT, WS, and I use the same idea that T is greater than S, you can say S is today, T is later, tomorrow. So you can say everything until today, until S, is the past. That is what we know already. That is information we have. And this property is telling us that when we go ahead from this point, yeah, and then look to this increment, WT minus WS, well, then this difference is independent what appeared last time or a year ago or whatsoever. The only information we have how this increment behaves is like property 3 is telling us. It's always normally distributed, expectation is 0, and the variance is defined as a time difference. So this, in other words, just means that when we are today, well, this process can go up or down. It doesn't matter when it goes up last period, that does not mean that now it continues going up, or when it goes down last period that it goes down. Well, we don't know. It is independent. What goes on next is independent from what was in the past, and it almost only follows the properties we set up in 3. And this is sometimes also referred as a kind of Markov property. Markov property. And we have so-called Markov processes, which is a generalization as well, but we will not talk about this. Yeah?
So if we go to practice, just to make another example, could you give us one where we use these Brownian motions? Because, like you said in the fourth property, actually it's independent of the past, or it has to be independent of the past, so we actually don't know how it's behaving. Like in the first graph you showed us with MATLAB, for example, there was this huge increase. So what are they used for in practice in finance today?
Well, here we are not talking about finance, we are not talking about special applications. This is a very abstract setup of rules. How a stochastic process should behave. And I say a stochastic process that follows these 4 properties is what I will label, or what we label in mathematics, a stochastic process. If it starts at 0, it's almost surely continuous, the increments are normally distributed with expectation 0, variance time difference, and the increments are independent from the past. The fourth property is just important because, think about, what we see in finance, obviously, is sometimes, well, the stock price goes up, right? And then, well, if the stock price goes up, you may say, well, it goes up further, which is sometimes a good proposition. And therefore, the stock price itself is not a stochastic process. And we will see this later on. I will talk about this. Because if it is a real stochastic process, you cannot say, well, if we are on this trend, on this uptrend, it continues, or when we are on a downtrend, it continues. That is what you sometimes do in finance. But this is contradicting this, right? Because here I say, at every time, I don't know. A stochastic process can go up or down according to 3. Expectation is 0. But I don't know the direction. There is no information about the past we use for saying anything about the future.
So that means basically I can't do any predictions. I can't make any predictions.
Well, yeah, we will see. Yeah, it's unknown, right? I don't know if I have a time series that is following a stochastic process. I don't know whether it goes up or down at any time. True. You know, in a discrete sense, you can say this is also what we call, or what you have called in other lectures, maybe a random variable or a random walk. Yeah, a random walk. Yeah. What we are talking here, when we talk about a Brownian motion or a binary process, is just the continuous description of a random walk, right? If you have a random variable, then you see the outcome this, and then you do it again, and then you have the outcome this. Yeah, they are discrete random events. And if you approximate this, you get a continuous process. And that is what we call, as I defined, a stochastic process. And a typical assumption we use for a random walk is the following. So, by the way, that's important to know. If you are once stopped by a policeman with your car and you are drunk, yeah, which is not good to do, obviously. And you know, I drink no alcohol, not due to that reason. It's just I'm convinced that is good. But if the case happens for you, not for me obviously, because it can never happen for me, but if it happens for you, I give you some advice. You say, well, the policeman is then telling us, so can I check whether you are drunk or not? And then please walk along this line, and there's a line on the sideway or street, let's say, and then you try obviously to walk straight, but you know it's it is a problem, and then the policeman say, well, that's not good, and then you just say, well, why? You see, sometimes on the left, sometimes on the right. In average, I'm on the line. And that is actually what this is telling us, right? In average, in the expectation, I say, well, we are straight. It could go up or down. I can walk left or right of this line. But in average, I'm straight on the line. And as long as this is okay, yeah, then we are in line with my property 3. But we can go up, yeah, that was your question. I don't know whether I walk on the left or right-hand side, yeah. But in average, it is staying on a line, like staying on the line, yeah. Or here 0. Okay, so these 4 properties, again, let me say this. These 4 properties define what we call a stochastic process, a Wiener process, or a Brownian motion. And keep this in mind, because I will come back, though property 3 is one of the key elements of this definition later on today. There is an interesting point which I have not mentioned so far, but last time, if you remember, we talked about, when I talked about the fundamentals of probability theory, we talked about probability space, right? And we said, well, usually we have a probability space based on my basic set omega, then we have a filtration F, and we have a probability measure P. And we call this set a probability space. And we even assume that my filtration follows 3 properties, which we discussed last time, and then we call this also a complete probability space. The Wiener process so far does not use the assumption of a complete probability space. So it's very general, and therefore sometimes difficult to understand. But later on, we will always assume here in finance that we work with a complete probability space. So there is a set, yeah. For instance, the stock price events, yeah, and we're just looking to the stock price, realistic stock price outcomes we are interested in our filtration, and there's a certain probability measure that gives us some probability on these stock price movements in the future. So we later on assume always a complete probability space here in class, but you can do further discussions on a more generalized level without this assumption. Question? No. Okay, so the next point is the following. I want to show you a very important linkage of a Brownian motion or a Wiener process to the idea of a martingale, a term we already talked about in the second week when we talked about risk-neutral probabilities or so-called equivalent probabilities or martingales. So let me show the linkage between a Brownian motion or a Wiener process and martingale.